Hello, and welcome to this hydropower seminar series of TGA and as part of Entrust Solution Groups. So my name is Jean-François Corbeil. I'm glad to present to you this small webinar. I'll start with a few words about me. So I'm a principal consultant at the Entrust Solutions Group. I have over 25 years of experience in the power generation industries. I specialize in hydro engineering, did a lot of operation of maintenance over the years, and I've been involved with a couple of merger and acquisition of hydro assets. I'm a professional engineer and a mechanical engineering in the province of Quebec and Ontario. Today, I want to cover three objectives with you. I would like to talk a little bit about the fundamental of hydropower, talk about the basics of hydroelectric plants, talk about the machinery mainly and maintenance and operation. And I will finish with what lies ahead in the hydropower industry. The outline of my presentation. So I'll start with what, why, and where of hydropower to explain a little bit about the concept of hydropower. I'll talk a little bit about the origin of hydropower, the main principle behind it. We'll touchly talk about the classification of hydropower, and after that I'll go deeper into the hydro plant, a little bit about the civil works, but mainly about the hydro turbine, and I'll touch briefly about the hydro generator and auxiliary systems. I'll finish by talking about maintenance and operation considerations and about challenges and opportunities in the hydro sector. So first, what really is hydropower? So this is a cross-section, if we can say, of a typical North American hydropower. It shows a hopper reservoir with a lower reservoir, which is usually the river on the tail race. The water passage will go through a set of trash racks to remove debris and prevent fish to go too much inside the penstock. Then the penstock will go into a scroll cage to distribute the water surrounding the turbine, and the water will exit through a draft tubes. The turbine will is connected to the generator by a means of a drive shaft. It will turn the rotor of the generator with the stator that is being fixed where the AC current will be generated, and then it will be go into the electrical conduit, the bus bars, with an elevation of the power voltage from the transformer. It will then, the electricity will then flow through the power lines. What really is hydropower? Hydropower, or we say also hydroelectric power or water power, is really the production of electricity by the force of moving water. This is achieved by converting the gravitational potential or kinetic energy of a water source to produce water. The main hydropower producer is China in the world, followed by Brazil, and United States and Canada are not far behind, with the third and being the third and largest and fourth largest producer. We say that hydropower is a clean energy, but why? Really, it's because of the hydrological cycle, the natural water cycle. So the water will pass through the turbine. It will go into the river or eventually reach the ocean. By evaporation from the sun, it will go into the atmosphere, will start to get condensation eventually, and will return to Earth under rain or snow. And then the cycle will continue like that. So that's why it's really a clean energy source. It's a very efficient conversion. We'll see later. It's around 90% of efficiency. It's a major technology that has been there for more than 100 years now. It has a long economic life. It has very low variable O&M costs. For sure, the fuel doesn't cost anything. And it provides a lot of ancillary services for the electric grid. And what are these ancillary services? It's, for example, to regulate the frequency, the 60 hertz that we have in our houses, and regulate the voltage and things like that. Hydropower is, by itself, it's rare that we find that in the world as being a standalone plant. Usually it's always part of the whole. And why that? Because it allows us to, for example, to control the flow of nature, prevent a flood. It allows us to do irrigation of the surrounding lands. It allows to have locks on river with navigation. It allows also to pond the water for drinking purposes. It will allow fish passages. And maybe the most well-known infrastructure that is part of hydropower is, for example, the Los Angeles Aqueduct, where there's a lot of hydropower in these penstock, but it's also used for drinking water. We find hydropower a lot in North America. It supplies about nearly 6% of all the electricity in the US and about 61.5% in Canada. And there's currently more than 2,000 hydropower plants with an installed capacity of 1 megawatt in North America. The origin of hydropower. So briefly, it's not new. It has started in the ancient world. It dates from the Greek civilization. It emerged also in China under the form of a water mill or water wheels. But it really took off in the late 18th centuries with the hydraulic power that has been provided by belts and drive shaft for mills. And by the late 19th century, the electrical generator was developed and could now be coupled with hydraulics. But it really took the World Fair at Paris in 1878, where people discovered the way to create light by electric lighting. It was not Thomas Edison at that time. It was the one that improved the technology just a year after that. But the people were interested to have light. So the world's first hydropower plant began operation in England in 1878. And really all it was able to achieve at that time was to light a single lamp. After that, the first commercial application with direct current occurred in Michigan in 1880, and the first alternating current commercial application occurred in 1893. And after that, it was one after another that all the plants started to be opening in the US and throughout the world. Just on a side note, the year 1882, so about the same time as the one in Grand Rapids, Michigan, saw the first two thermal power plants being commissioned, the one in London and one in New York. So really at that time, it was a very interesting time to see new technologies. Hydropower is achieved by two main factors. To produce the power, we need the flow and we need the head. So we need the volumetric flow, which is here, that will pass through the penstock, and the difference of height that we call the gross head between the headwater and the tail race. These two combined together with the gravity will give the power that we can obtain. And in total, with all that, we talk about 90% efficiency from the water to the electron, so which is very good. There's different classification, and I won't go into all of them, but just to go with the two major ones, one is based on the power that we can achieve. So usually we talk about a large power plant like the one here in Hoover Dam. It's above 50 megawatt of capacity. A medium would be between 10 and 50, like this one in Virginia as an example. And for residential use, if we can say, we have micro hydro. The other factor that is important for classification is the head of the power plant, not the power plant, but the penstock or the capacity of the plant. So we will talk about high head, which is more than 100 meters. It's something that we can find, for example, in the Rockies mountain. So this is a typical of a high head. And low is more what we can find, for example, along the Mississippi River. And very low, it's rare, but it's for small projects where there's a high capacity of flow, but very low head to drive a turbine. Another classification for hydropower is what we call conventional hydropower, which has been there since the beginning of the industry. And there's really two major categories here. The first one is a run-of-river. It's a project where we have no water storage or very little because there's just a small impoundment that will be made. And the power then has no choice than to vary based on the flow available. It doesn't allow to have a firm capacity for pricing, for example, and to be able to deliver electricity on a need basis. If there's a drought, then we cannot generate too much electricity. On the opposite, we have what we call a reservoir or an impoundment, what we see in large projects usually, where we have a dam that will store the water and provide baseload power with the ability to start and stop on short notice. One of the most known project for a run-of-river, people maybe are not too much aware of it, but it's the Niagara Falls. People are used to go there to witness the falls, and that's very nice, but without knowing that in fact there's three big hydroelectric plants just downstream of the fall. One on the US side that is called Robert Moose's, and two on the Canadian side that are called Sir Adam Beck 1 and 2. And they take the water from tunnels that are dig under the town of Niagara on both sides of the border. But there's still enough water to pass over the fall. And all it was required was to construct a small dam here, control dam, to manage better the flow for the generating station. For a reservoir, a nice example is the Grand Coulee Dam in the state of Washington, where it has which is the biggest hydro dam in the US. If we continue along the classification of hydropower, the other kind of typology for hydropower, we can find pump storage. Really, what is pump storage? We need two reservoirs, an upper and a lower, and during the day, the water will go down from the upper to the lower, generate electricity to assess the need of the population during the day. And at night, when the electricity cost is very cheap, they will return the water from the lower reservoir to the upper by pumping. Another kind of hydropower that is more and more popular these days is the marine and hydrokinetic, something that we can find, for example, in stream of rivers or along the coast, where we can construct a tidal barrage, for example, and the water will go through a turbine in and out based on the tide of during the day. And another small type of hydropower is what we can find in Kundry. For example, on aqueduct, it's kind of a small windmill that we can find inside a penstock or pipeline. Now I would like to go a little bit deeper into an hydro plant. So I'll touch base on the civil works, on the hydro turbine, on the hydro generator, and a little bit about the auxiliary systems. To do an hydropower plant, we need civil work, we need infrastructure, and for that, civil works represent more than 50% of the initial investment. I'm not civil engineer, but I will just touch a little bit on these aspects. So we need a diversion dam. It can be just a low height dam for run-of-river facilities to a very high capacity dam, as we have just seen. The dam can be made of concrete, masonry, wood, which was a popular material in the time, and sometimes from earth for the core of the dam. It requires also a spillway or gates to be able to evacuate water. We never know, we can have a flood and then we need to evacuate some water. We need also water passage from the intake to the tail race, and this water passage can take the forms of a canal, an underground tunnel, or a penstock. It will require a valve to control the flow, and also to isolate the gates to perform maintenance on them. We will need also a powerhouse that will house the turbine, the generator, the mechanical and electrical equipment, and the powerhouse can be above or underground. And on the outside, we will need a substation with a switchyard and a transformer. Here's a typical, it's a nice representation I found that shows the main gate in the hydro projects. We can find, for example, radial gates, which are very popular for a certain type of dams. We call them also tainter gates. We can have also a roller gate that are like a slide gate to operate and pass the flow through the dam. We can have also rubber dam, which is essentially a big inflatable rubber bladder that can be deflated to pass the flow. Sometimes we can find for older dams, mainly stop logs that are made either from steel or from wood that will be stacked to create a gate. And we need a bulkhead from time to time to be able to do to cut the water passage at the entrance and at the exit to be able to do maintenance on the system. We can find also major valves in power plants. These are mainly required for penstock. At the entrance, we will find either butterfly valve or spherical valve. And we will need also an energy dissipating device because the pressure will be built along this penstock. And we need, if we have a shutdown of the turbine, to be able to dissipate this energy. So from time to time, we will find at the exit of a plant a cone valve to dissipate the energy. And sometimes we will find also surge tank. Here we have an embedded penstock underground that we cannot see, but we have a surge tank. So if we shut down the turbine very rapidly, then the amount of extra water, extra pressure will go into the surge tank and dissipate there. We need also trash racks because there's always debris on the river, especially when we are close to towns. There will be a lot of floating wood or other kind of debris. And we have also the fish population to control. So we will have to put a trash rack at the entrance of a penstock, for example. And to remove these debris, well, we will use trash rakes. Sometimes it can be just a manual rake, but sometimes it requires big machinery like this one. And another infrastructure that is required is fish passages. We don't find that on every power plant, but most of them, and especially now that there's a big push to restore rivers in our ecosystem. So we will find for moving the fish upstream, we can find fish ladders, for example, like this one in Boonville Power, where the fish will simply jump from one bucket to another to return to the upstream side. We can find fish lift, for example, or a climbing ramp for hills. So they will we will see the hills sliding through the mats made of spikes. And to move downstream, we will have spillway with minimum flow requirements. For example, to pass a certain amount of fish, we will open gates. We can have bypass pipe for that. And what is the latest technology is to improve the turbine design, to allow the fish to pass through the turbine without being damaged or killed. So that's the newest way for that. Talking of turbine, we'll go into that in a minute, but just with this nice picture, we have a good cutaway of a hydro plant. So we will have we see the water coming from the penstock going here into the intake of the turbine, and I'll just go to the next slide that shows a bigger pictures. So the water will pass through a certain will pass through a stay-vane ring, which are fixed, and then through wicket gates that act as a big faucet. We can control the wicket gates opening. And the wicket gate is controlled by this orange ring here. We call it the wicket gate ring. or bell ring. It is actuated by a servo motor, which will control the amount of water that can go into the turbine. The water will pass through the runner here, number 6. In this case, it's a Kaplan because we see that it has a variable pitch for the blade. The pitch for the blade is controlled completely at the top, number 10, what we call the Hoy head. So we have a set of shaft that will drive with a piston acting here, a set of mechanism to operate the blade opening. So the energy that is being converted from the kinetic energy will go through the main shaft, number 7, and drive the rotor of the generator, number 8. On it, we will find a north and a south pole on the periphery with salient pole, and these poles are being operated, if we can say, by a DC current. We need a certain set of DC current to operate a hydro plant. So this energy can be found from batteries, for example, to generate this DC current. And when the DC current passes in front of the stator, number 9, it will generate electricity on the AC with a low voltage. A low voltage. So the voltage will have to be raised by going through the transformer eventually. To keep the generator cool, because there's a lot of energy being dissipated in thermal energy, we will find a cooler, air cooler or water cooler here. And all the weight of the turbine and generator rotor is taken by the truss bearing that we find at this level. Usually it's on top or just below the generator. And so that's the main component of a hydro turbine and generator. If we go a little bit deeper on the turbine, there's 2 major classes of hydro turbine. The first one is an impulse turbine that extracts the energy by reducing the fluid velocity. We will use a jet, for example, to act on a blade, and the blade will rotate with the runner. We operate this kind of turbine at atmospheric pressure, and we really use that when there's a significant amount of head. Reaction turbine, it extracts the energy by reducing the fluid pressure, so it operates under pressure, and there's a pressure drop along the rotation, and that converts into kinetic energy. We can have axis of rotation either vertical or horizontal. Horizontal, we find that more for smaller projects. A little bit more about the impulse turbine. So the most popular type of impulse turbine are either Pelton or cross flow. Pelton is really for high head and low flow projects. And we can find a runner with several jets. Like here, there's 2 jets that will inject the water on the runner that has several buckets to recuperate these water impulse. A cross flow it has a runner that is similar to a squirrel cage, and the water will pass through it on the way in and on the way out. So it creates the energy that way. This is really for smaller projects and higher flow. On the side of reaction turbines, we find Francis turbines. Francis turbine it has a runner with fixed blades. The water is introduced uniformly around the periphery of the runner by the way of a spiral cage that will distribute the pressure equally, and the pressure will drop significantly through the water will drop in pressure significantly by passing through the runner, and we can use the draft tube to extract even more power. The other type is a propeller. A propeller, it's similar to a boat propeller in a pipe. It has a fixed blade usually, and then we can add different configuration. And the most popular configuration these days is a Kaplan. A Kaplan is simply a propeller, but with variable pitch. And here again, we have a depiction of a typical Kaplan turbine, and the wicket gate will be adjustable, and the blades will be adjustable. If we resume all these turbine type into a chart, we will find something like this. A turbine selection chart where we find, for example, on high head project and low flow, the Pelton turbine, and on the opposite, on low head project with high flow, we can find a Bell turbine or a Kaplan turbine for that. And the Francis are usually in between. The main criteria when doing a project is to select a proper rotation speed, to select what would be the best way to extract the efficiency, what will be the annual production that we want to achieve, and the cost of construction. It's important to note that a Pelton turbine can be put on the ground level, but to be efficient, a Francis or even a Kaplan need to be put underground as much as possible to extract the more power and prevent cavitation. We'll go into that soon. So that will drive the cost of construction if we have to do excavation. In terms of efficiency, each turbine will come with that kind of chart that we call a hill curve chart. It has the head here on the y-axis, and on the x-axis we have the discharge, the flow. And we have on these diagonal lines, we have the guide vane opening, the wicket gate opening. And we have different curves of efficiency. And when we look these curves in the 3D, we find that it's like a hill. So the biggest efficiency will be in this area, for example, for this turbine. The way to read that is, say we operate at 25-degree opening along that line, and we have a head of 52.5 meters. So we'll be able to pass 9 cubic meters per second, and this will give an efficiency close to 89%. If we take this same chart and we go along this line for a certain head, we will find a power curve here, for example. These are all power curves for Francis turbine operating at different flow, at different heads, sorry. And when we assemble all these Francis turbine, we can compare that, for example, to a Kaplan turbine that will have a much horizontal power curve. So we have more efficiency on a long range of flow as compared to a Francis turbine that will operate at the peak efficiency only on a certain specific amount of flow. So this allows us to compare easily a Kaplan from a Francis turbine. If we look at the major components of a turbine, we'll find for sure the runner. The geometry is optimized by CFD analysis and model testing. From the model testing, they will create the O&M will create a runner that will be put into a project, and they will achieve at the end of the project field testing. And for that, it's important to meet the warranties expected by the O&M. We can have, as mentioned, fixed or variable blade. We can find internal mechanism for blade pitch that will be controlled by a hydraulic system. Sealing is something that is important for the blades here because it won't last forever. They will need to change that. So more and more the technology is to go from oil fill runner to air fill, just compressed air, to prevent water from oil to go into the water of the river. We will have eventually we will find wear between the blades, the blade tip, for example, and the fixed rings. So that will be important to investigate over time. And what is important, especially for Francis turbines, since there's a significant amount of pressure drop, is the cavitation. And here's an example of a cavitation damage on a runner. And cavitation is simply a brief change of state of the gas from the water liquid to gas due to a drop in pressure. And by doing this change of state, it will pull the material out of the blade. So eventually we'll find holes in the blades. Another significant component that we talk a little bit is the wicket gate ring that we find here, the blue color. It's a control ring to which is attached all the wicket by way of a linkage rod. And each wicket gate that we can find here has a break-in pin or another device to be able to free the gate and prevent breaking the wicket gate shaft. Say, for example, a significant debris goes inside a penstock. You don't want to jeopardize your complete set of wicket gate. So you will have a shear pin, for example, that will break to free the wicket gate and prevent further damage. All these wicket gates and the wicket gate ring are controlled by a servo motor that can be operated by water or by a hydraulic system. In the past, we were talking about governor or HPU. It's what we use the most in smaller projects. Another major component of hydro turbine is the shaft line and the bearings. We find usually a turbine guide bearing at the bottom, another one underneath the generator, and one above. And all the weight of the shaft line is taken by the truss bearing, which is usually underneath the generator or above the generator. Here, sometimes we talk about a combined bearing because we can find the truss and the guide bearing together. This, for example, is a location where we will find a significant amount of oil bath. The bearings will will be in a oil bath, and the oil bath will have to be cooled, for example, by water to prevent overheating of the bearings. The bearings use most of the time tilting pads. They can be made of babbitt. Now it's more and more often that we find Teflon or composite material for that. Another significant important area on the shaft line is the coupling. Here and also the generator, it's important to have a look at the bulbs from time to time. So the key aspects of the shaft line are the alignment, the vibration, and the temperature that will be monitored throughout the operation of a project. Now on the generator side, there's different kind of generators. The most popular one is that we find in big projects mainly is a synchronous generator with salient pole. Here's an example of a salient pole. So all the poles are exposed on the surface of the rotor. We will have a north and a south, a north, a south, etc. And they are driven by a DC excitation. So there will be a DC exciter somewhere in the power plant, and from brushes, the current will go on the shaft, and from the shaft it will connect to the lead of a generator pole, and then all the poles will be connected together. So this excitation will provide a magnetic field to create the north and the south pole. Another kind of generator that we find mainly for small hydro plant is an induction generator with a permanent magnet type. Usually it's for projects of less than 8 megawatt. It requires, however, power converter to better control the power factor. And now with the new technology that has been implemented mainly from pump storage hydro, we will find induction generator, double fed type that we say, with AC excitation. So in this case, we need a lot of copper on the face of the rotor to be able to have this AC excitation. We can have different kind of configuration. Most of the time it's a direct drive with the runner, but for smaller project where the runner goes at the high speed, we will need a speed we need a speed increaser, the runner with a gearbox for smaller unit to generate the electricity, not a speed decreaser, but increaser. Sorry. And all of this, more and more, the power electronics is important to modulate the parameters during operation. Finally, in a power plant, we'll find a lot of other systems. We briefly talk about the cooling water system that is used for mainly the extract the heat from the bearings and also from the generator. We will find also a potable or filtered water system that is used mainly for the shaft seal. Shaft seal, we can find that at the base of the rotor here, just above the guide bearing, or below the guide bearing, sorry. It's to make sure that we separate the water pressure from the water passage from the atmospheric pressure of the power plant. So this seal is very important, otherwise we will flood the powerhouse. So for that, usually we inject a small amount of water to make sure that the seal is tight. We will find also in a powerhouse a fire protection system. compressor system also that will be required for braking the generator. Sometimes we will find under the generator rotor a set of brake pads that will lift the whole assembly to make sure to brake it. The turbine dewatering system is important because otherwise the runner will remain in water all the time, but we have to do some maintenance there from time to time. So we will close the gates at the upstream and downstream and use a pump to drive out the water. There's frequently oil leaks or debris like that comes from the various oil system. So there will be a powerhouse drainage that is required. There's also water leaks. And for that, we will have a kind of a oil-water separator to manage the sewage and the waste from the power plant. And we'll need also a HVAC system, otherwise the whole power plant will be too humid over time. If we talk about the maintenance now of the turbine and generators, these components are usually designed with a long life expectancy. They are designed certainly for 30 years and even more. But what happens from time to time is that there will be some infant mortality in the early years. So we will need some debugging or improvement in the first few years to make sure that the plant is reliable. After that, the maintenance really is a function of the type of use. Some plants will be used just for peaking. Sometimes we'll run 24 hours, 7 days a week, all the time. So really, it's not the same kind of maintenance that will be done on these two types of power plant. There will be also some insurance requirements. We will have also dam safety requirements coming from the regulatory agencies, doing mainly for inspection of civil structures and also for the gates. And it's all based on industry best practices and based also on past and known issues that we have had with the equipment. The maintenance of a turbine and generator, we can divide that maybe also in 3 categories. So there's the routine maintenance that we do when the turbines are operated. So it doesn't require any outage for that. So in terms of oil, we will need oil filtration, for example, check the oil levels, change oil from time to time. Usually we'll wait for an outage to change the oil. We'll check for leaks. As I mentioned, there's frequently water or oil leaks. We will need to adjust the cooling system, make sure the cooling systems are clean. And what is really important, especially for smaller projects, is to detrash in front of the intake. Otherwise, the intake will start to be blocked and the pressure will increase in the and differential from one side of the intake to the other side, and that will reduce significantly the amount of power that can be produced. For more maintenance, we need to do an outage for that. That will occur maybe once a year or once every 2 years. For that. Sometimes it can be pushed back to 5 years, for example, and that requires to dewater the water passage. So at that time, we want to focus on the shaft line, measure the gaps at the blade tips and the bearings. Sometimes we will need to do some NDT inspections on the blades, on the shaft, for example. We will measure the gaps also at the wicket gates, make sure that they all close appropriately. We will check the seals. It's important to replace them also at a certain time interval. We'll check for cavitation. We'll perform electrical tests on the generator at the same time. And also we'll check for bolt torque and insulation condition everywhere on the turbine and generator. These machines operate a significant amount of speed where the centrifugal force is significant, and you don't want to create more damage if something becomes loose. We also will plan for significant maintenance on a plant outage. At that time, that requires engineering. We will replace or rebuild the wearing parts at that time, such as the wearing rings between the runner and the fixed parts. We will replace the bushings of the wicket gates. We will replace the seals, check and confirm that the truss bearing pads are still in good condition. Now we'll jump into the operation. Most of the operation these days are done remotely. In the past, there was always personnel on site in the old power plants because they were old, they were not, there was not enough instrumentation, but nowadays we try to operate remotely, and we'll keep the maintenance personnel on site only when is needed. We will rely on the SCADA or DCS system for that acquisition of the power, the flow, the pressure, the temperature, and the vibrations. We'll be able to stop and start every unit from a distance, and we will rely on alarm notification system and video surveillance camera. And when something happens, we'll send the maintenance crew on site. Only for the operation, what is important, most important thing is really to control the flow at a water project. And that is important because of dam safety aspects all the time. If there's a flood, you want to be able to plan in advance and evacuate the flow. And also you have to respect the minimum flow requirements for the fish and wildlife. You need to also obey to the rule curves. Rule curves are generally created to make sure that the water projects operate a certain condition to the benefit of everyone on the river system. So this is an example at the Seneca Lake in New York State, where the elevation before the plant will have to be within a certain target for a certain month of the year, and it will increase for the summer, usually for boating reason, and it will reduce during the fall because we know that we will need a significant amount of capacity comes the spring to evacuate the water. We will also operate the turbines to make sure that we have the best efficiency. Ideally, we want to operate as much as possible, close to 95% at all the time, but it's not always possible, depending on the type of turbine that we have, and also the number of turbines that we have in a plant. So we will have to check what is the best efficiency for the whole project. Another aspect that will be important, not all power plants have power purchase agreement with a fixed amount of dollar per kilowatt hour. So sometimes the projects, they generate electricity and they sell that to the energy market. And the wholesale electricity price fluctuates all the time. So you want to make sure that during the day you will be able to spot and generate electricity at that time to maximize the revenue of the plant. Before I conclude, I would like to talk a little bit about the current challenges and opportunity in the hydro world. Right now in North America, we have an aging fleet of hydro plants. The average age is close to 40 years. So that creates a lot of struggling for operators to find the spare parts. And for that, they need sometimes to think about modernization of their plant. So major overhaul will be needed. Also, at that time, they didn't have all the drawings necessarily available and not all the instrumentation. So there's a lot of work to be done to digitalize the infrastructure a little bit. And for that, instrumentation and AI will be used to improve the O&M. The power system is changing also. We go more and more from base load to peaking with ancillary services. So we need to plan ahead for outages in order to be able to be efficient. And sometimes we have no choice than to extend the life of the equipment. So that drives more wear and tear on the equipment because there's also more start and stop. So we have to take that into consideration and plan for a redesign of the plant by adding this flexibility and also think ahead by having other kind of technologies like pump storage capacity, having hybrid hydropower. For example, here's a floating solar project close to a hydropower dam. So we will be able to take the energy of the sun during the day to maximize the output of the plant. And that also helps to reduce the evaporation of water. The climate is changing and we want to go towards net zero energy. So it's contradictory. So we'll have more and more droughts and flood. Here's an example of Lake Oroville between August 2021 and March of last year. So we have to be flexible in terms of asset management, in terms of smoothing the peak of consumption. So adding more pump storage will be needed. And finally, there's a lot of push for environmental and social acceptability. We need to take care more about the resource. So technology towards fish-friendly turbines, oil-free turbines, and fish passage are just good things that will come ahead. And this will allow fish like this one. We don't see it too much, but there's certainly a smile on his face. In conclusion, can we buy a hydro turbine on Amazon? Certainly not. Hydropower projects are complex. They involve many disciplines, as we have seen, civil, electrical, mechanical. There's a lot of stakeholders involved. There's a lot also of regulations. And there is no one size fits all. But hydropower is really needed in the energy mix. And although there are several challenges lies ahead, it will require many iterations. And that's why it requires experts in the field. And Trust is there to help anyone in the hydropower business for advice in terms of hydropower projects. So I thank you of your time listening me. If you have any question, I'll be pleased to listen to them.